Light is the fastest thing that exists. Yet for light, no time passes at all. Not a second, not a fraction of one. Every beam crossing the universe experiences zero duration between the moment it's born and the moment it dies. Physicists confirmed this using Einstein's own equations in 1905. And most people still assume light experiences its journey the way we do. The light from the sun takes 8 minutes and 20 seconds to reach your eyes. GPS satellites lose 38 microseconds a day to this same effect. And, uncorrected, your phone would be 6 miles off within a day. Light from the most distant galaxy ever photographed has traveled for 13.4 billion years. And for the light, that trip took no time at all. Tonight, we'll uncover why Einstein called this the strangest consequence of his own theory. What a physicist named Rietdijk proved about your future already existing. Why atomic clocks flown around the world in the Hafele-Keating experiment came back, changed, and the one paradox even physicists still argue about. By the end of tonight, you'll understand exactly why the light entering your eyes this second has never once experienced a single moment of its own existence. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. And before we begin, leave a comment with where in the world you're settling in tonight. When you wake up, you'll find the others who drifted off under this same impossible light. Let's begin. Look at whatever is nearest right now. A hand, a lamp, the corner of a room, none of it is being seen as it is. It's being seen as it was a few billionths of a second ago, the time its light took to cross the small space in between. That gap is too small for a human nervous system to register. It stops being too small very quickly. The sunlight warming a windowsill left the surface of the sun 8 minutes before it landed there. A fact so often repeated it has gone numb, said so many times that the strangeness has drained out of it. So set the sun aside for a moment and look up instead, on a clear night, at a single reddish point near the shoulder of a hunter-shaped constellation, Betelgeuse, a star roughly 640 light-years away, swollen and unstable, and by most estimates within the next 100,000 years of ending its life in a supernova bright enough to see in daylight. Here is the sentence most documentaries stop at. It might have already happened. The light leaving Betelgeuse tonight left it 640 years ago, and there has been no way, since then, for anyone to know what the star is doing right now. Except that sentence is not quite true, and the reason is stranger than the not knowing. Right now is not a small, forgivable uncertainty waiting for a faster telescope. According to the physics behind the GPS system in every phone on Earth, two events separated by 640 light-years do not have a single, agreed upon, at the same time for anyone to eventually discover. Different observers, moving at different speeds, will order the star's death and this exact sentence differently, and the theory does not call either of them wrong. Stay with that for a moment. It means the question, is Betelgeuse dead right now, is not a mystery science hasn't solved yet. It's a question built on an assumption, that right now reaches across 640 light-years the same way it reaches across a kitchen table. And the assumption is the part that breaks. Physicists call the region where now still behaves normally a light cone, close enough, in space and time, for the word to mean something ordinary. Step outside it, and now stops working the way it was always assumed to, at a distance small enough for light to erase in an instant, which is where this stops being merely astronomical. Every now a person has ever felt, the ordinary, confident sense that a room and the thoughts inside it are happening together at once, has only ever been tested at distances where light's delay is too small to notice. It has never once been verified at a distance large enough for the delay, and the disagreement it causes, to show. That's the crack this whole night walks through. Not whether Betelgeuse is dead, whether at the same time ever meant what you thought it meant. For anything, anywhere, including you. Here is the instinct almost everyone reaches for, and it is a reasonable one. Maybe none of this is happening to time at all. Maybe it is only an illusion of measurement. The way a river can look like it's flowing backward from the deck of a faster boat. Perspective plays tricks. Surely time dilation is just a trick of vantage point, not a change in the thing itself. That instinct is the first thing tonight has to take apart, because for almost 2 centuries of physics, it was correct. Every kind of relative motion anyone had measured, trains, cannonballs, planets, obeyed a simple rule. Speeds add together the way you'd expect. Throw a ball forward from a moving train, and its speed relative to the ground is the train's speed plus the throw. Addable. Ordinary. Nothing about it insisted that time itself had to bend. Then physicists measured the speed of light from every direction they could arrange, moving toward it, moving away from it, at every season of Earth's orbit. And the number never changed. Not add, not subtract. The same number every time, regardless of how fast the thing measuring it was moving. Picture a clock made of nothing but a single flash of light, bouncing forever between a floor mirror and a ceiling mirror 1 foot apart, each round trip counting as 1 tick. Standing beside it, you would see the light travel a straight foot up, a straight foot down, tick, 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 steady as a heartbeat. Now put that same clock inside a train, racing past at a large fraction of light speed, and watch it through the window. From that outside vantage point, the light isn't just going up and down anymore. The whole clock is moving sideways while the light bounces, so the beam has to travel diagonally, a longer path than the one measured standing beside it. Longer path, same speed because light does not get a discount for being inside a moving train. And a longer path traveled at a fixed speed can only mean one thing. More time has to pass, on the outside, for each single tick the clock completes. The clock is not confused. Riding along beside it, its flashes hit the mirrors exactly as they always did. 1 foot, 1 foot, tick. Only from outside the glass, watching a beam forced onto the longer, diagonal road, does its ticking visibly slow. 2 different, equally correct counts of how much time passed, from 2 different points of view, and nothing broken, nothing tricked, just 2 different paths for the same unbending speed. Not an illusion of the eye, a fact about geometry, forced into existence by a single stubborn number that refuses, in any reference frame ever measured, to add or subtract like everything else in the universe does. But a thought experiment involving a train and a mirror is one thing. Somewhere, something real had to actually slow down. On a clock nobody was watching through a window, and in the early 1960s, that something turned out to be falling out of the sky by the billion, every second, onto a mountain in New Hampshire. In 1963, 2 physicists, David Frisch and James Smith, carried a particle detector to the summit of Mount Washington, New Hampshire, and set it counting a kind of subatomic rain that is falling on you right now, whether it can be felt or not. High in the atmosphere, cosmic rays slam into air molecules and shatter into short-lived particles called muons, heavier cousins of the electron, born roughly 9 miles above your head. A muon lives, on average, 2 millionths of a second before it decays into nothing. 2 millionths of a second is not enough time, by any ordinary arithmetic, for something to fall 9 miles, even close to the speed of light. Do the multiplication the old way, the way Newton would have done it, and only a small fraction of the muons created up there should ever survive long enough to reach the ground. Frisch and Smith counted the muons arriving at the summit. Then they carried the same detector down to a basement in Cambridge, Massachusetts, near sea level, and counted again. By the old arithmetic, the count at sea level should have collapsed to almost nothing, most muons dying somewhere in the miles of air between the summit and the valley floor. Instead, The detector at the bottom counted far more muons surviving the trip than classical physics allowed. Not a small discrepancy, a number roughly 9 times higher than the old equations permitted. 9. Hold that number. It is not a flaw in the detector. The muons were traveling at around 99.4% of the speed of light, fast enough that, from the ground's point of view, their own internal clocks, the delicate subatomic process counting down to decay, ran slower by almost exactly that same factor of 9. The particles were not cheating physics. They were living inside a slower version of the same 2 millionths of a second everyone else uses, stretched by their speed into enough borrowed time to finish a 9-mile fall. So the mirror clock in a train car and the muon falling from the sky agree. One imagined, one counted on a mountain. Speed changes how much time passes, for real, independent of any observer's confusion or any trick of the eye. That much is no longer theory. It has been measured on a mountain, in a basement, decades before this sentence was written. Roughly one of these muons passes through the palm of an outstretched hand every minute. Right now, in this room, borrowing exactly the same stretched fraction of a second, the ones over Mount Washington borrowed 60 years ago. A small, constant, invisible rain of stretched time falling on anyone who happens to be lying still beneath it. But 9 is not infinity. The muons that fell onto that mountain were moving faster than almost anything you will ever personally encounter, and still only borrowed 9 times their ordinary span of time. Their clocks slowed. They did not stop. And a muon, unlike the thing promised in tonight's opening minutes, has mass. And mass sets a hard limit on how close to the speed of light anything will ever actually get, no matter how much energy is poured into it. Something without mass does not have that limit. And what happens to a clock when the speed pushing it slower is not 99.4% of the way there, but all the way, is a question no muon, no mountain, and no basement in Cambridge has ever been fast enough to answer. 60 miles outside Geneva, in a tunnel buried 300 feet under farmland along the Franco-Swiss border, engineers have spent more than a decade trying to do one thing to a proton: make it go faster. The tunnel belongs to the Large Hadron Collider, and inside it, protons circle a 17-mile ring, gaining energy with every lap, chasing a target they were never going to reach. At full power, those protons travel at a speed so close to light's own that the shortfall is written in zeros. 0.9999999, 7 nines before the number finally changes. From the proton's accumulated energy, physicists calculate that its internal clock, whatever mechanism inside a proton counts as a clock, would be ticking more than 7,000 times slower than a clock sitting still beside the tunnel wall. 7,000 times, and still short. The whole facility draws something close to the electricity of a mid-sized city. Nearly all of it spent narrowing a gap that keeps refusing to close. You have felt a smaller version of the same shape of problem, in miniature, any time you have watched a phone hunt for a weak signal in a basement. The closer the device gets to a stable connection, the more battery it seems to burn, chasing the last little bit, as if that final sliver of the job was somehow more expensive than all the rest of it combined. In the tunnel outside Geneva, that somehow turns out to be a hard, provable law of nature, not a quirk of engineering. But here is the part almost no popular explanation says plainly. The reason no accelerator on Earth will ever finish that last fraction of a percent is not a failure of engineering. It is not a matter of stronger magnets or more electricity than the tunnel currently draws. Every additional watt poured into that proton buys a smaller and smaller sliver of extra speed, and the pattern does not bend toward an achievable finish line. It bends toward one that recedes forever. Closing that final gap would not cost more electricity than humanity has ever generated. It would cost an infinite amount, because the relationship between energy and speed, for anything with mass, is built so that the finish line does not exist for a moving object made of ordinary matter. Not because the tunnel isn't long enough, because the price of the last inch is not a bigger number. It is no number at all. So the fastest thing humanity has ever deliberately accelerated has still never once traveled at the speed the sunlight on your skin manages by simply existing. Every proton in that 17-mile ring, straining against 7,000-fold time dilation and the full electrical output of a small country, remains, by the only measure that matters, slower than a beam of light idling out of a lamp across the room, which means whatever is about to be said in the next few minutes about what light itself experiences cannot come from a detector, a mountain, or a tunnel under the Alps. No instrument has ever ridden alongside a beam of light to check. Every answer that follows comes from somewhere stranger than a laboratory, from a single, impossible daydream, worked out by a teenager who wasn't yet allowed to call himself a physicist. In 1895, in a small Swiss town called Aarau, a 16-year-old student who had recently dropped out of a school in Munich sat with a question he could not put down. What would it look like to run fast enough to keep pace with a beam of light? Not as a figure of speech, as a physical question, with a physical answer. If light is a wave, the way physics of the era described it, then catching up to it should freeze the wave in place. The way running alongside an ocean wave at exactly wave speed would let a swimmer watch a single ridge of water hang motionless nearby, stand right beside a beam of light, moving at its exact speed, and by that same logic the result should be a frozen, unmoving pattern of electric and magnetic field going nowhere. But nothing in the physics he had been taught allowed for a frozen beam of light. Light that isn't moving isn't light at all. The entire mathematical description of it depended on it moving, always, at one particular speed. A stationary light wave wasn't a strange kind of light. It was a contradiction with no physics behind it whatsoever. For the better part of a decade, that daydream sat unresolved in the back of a mind that would eventually become one of the most recognized in the history of science. Not because the young Einstein lacked the mathematics to work out an answer, but because every honest attempt at one broke something else. Assume the chase could succeed, and the equations describing light stopped making sense. Assume it couldn't, but then what, exactly, would stop it? Nothing in Newton's universe forbade it. Add enough speed to anything. On paper, and eventually, the gap should close. By 1905, working as a patent clerk in Bern rather than as a university physicist, Einstein published the answer, and it did not resolve the daydream. It deleted the question. His second postulate stated, without apology, that the speed of light is the same for every observer, regardless of how fast that observer is already moving. No speed is fast enough to reach it. No train, no rocket, no future machine will ever see a beam of light slow down, freeze, or fall within reach. Chase it at any speed at all, and it still recedes at precisely the same rate it always did. From you, from a rocket, from anything. The daydream had asked what the runner would see, riding alongside light. The answer, decades later, was that riding alongside light is not a difficult trick. It is a sentence with no meaning behind it, grammatically fine, physically empty, like asking what color a number is. And that emptiness is not a flaw in the question. It is the first real clue, buried in a bored teenager's daydream, that light's own experience was never going to behave the way yours does, because there may be no riding alongside for light to ever be caught inside of. In 1887, in a basement laboratory in Cleveland, Ohio, two American scientists built one of the most sensitive instruments of their era to measure something that, as far as either of them knew, absolutely had to be there. 19th century physics assumed light needed a medium to travel through, the way sound needs air, an invisible substance filling all of space, called the luminiferous ether. If the ether existed, and the Earth was ploughing through it at roughly 18 miles a second in its orbit around the Sun, then light should travel very slightly faster in the direction Earth was moving through the ether, and very slightly slower against it. The way a swimmer crosses a river faster going with the current than against it. Albert Michelson and Edward Morley built a device precise enough to catch a difference that small. A split beam of light, sent down two perpendicular arms of equal length, reflected back and recombined, watching for the faint interference pattern that any speed difference between the two directions would leave behind. They ran the experiment at different times of day and different seasons of the year, rotating the entire apparatus on a bed of liquid mercury to cancel out any bias in the equipment itself. They found nothing, not a smaller effect than expected. No effect at all. In any direction, at any time of year, the light took exactly the same time down every arm, regardless of which way the Earth was supposedly ploughing through the ether that instant. The experiment would be remembered as the most successful failure in the history of physics, though neither Michelson nor Morley would live to see why. For nearly 2 decades, the null result sat as an embarrassment. An anomaly physicists tried to patch with increasingly strained explanations. An ether somehow dragged along with the Earth, lengths that contracted in exactly the right direction to hide the effect. Anything to save the assumption that space needed a medium and light needed a favored direction. None of this should feel abstract or far away. Right now, you are moving around the sun at roughly 18 miles a second, spinning with the planet beneath you, drifting with the entire sun around the center of the galaxy at a still faster clip. Layers of motion stacked on top of each other. All at once, all the time. If an ether existed, that motion would mean ploughing through it constantly, from every direction, for the whole of your life. And yet nothing about the way light behaves around you, ever, in any careful measurement, betrays a hint of it. Then, in 1905, a young patent clerk in Switzerland offered a different explanation, one that didn't try to save the ether at all. There was no ether to detect because the speed of light isn't measured relative to some hidden substance filling space. It's the same in every direction, for every observer. Full stop. Not because the Earth happens to be moving in a way that hides the difference, but because there is no difference to hide, anywhere, ever. The basement in Cleveland hadn't failed. It had accidentally proven, a full 18 years early, the one experimental fact that made sense of the daydream in our owl, that nothing, moving at any speed, in any direction, will ever catch light slowing down for it, return to the mirror clock from earlier. The beam of light bouncing between a floor mirror and a ceiling mirror, ticking once per round trip. Outside the train car, watching it rush past, the beam has to travel diagonally, a longer path forced by the sideways motion of the whole clock while the light bounces up and down inside it. Longer path, same fixed speed, so more time passes outside for each single tick recorded inside. Now push that thought experiment as far as the mathematics will honestly go. As the train's speed climbs toward the speed of light itself, the diagonal path the light has to travel from an outside point of view stretches longer and longer, approaching something strange, a path so close to horizontal, so nearly parallel to the direction of motion, that the light inside the clock is doing almost nothing but keeping pace sideways with the train, barely making any progress at all between floor and ceiling. Follow the equation all the way to the speed of light exactly, and the outside observer's count of elapsed time for even a single tick does not simply grow large, it grows without any upper bound at all. The formal way of saying an infinite amount of outside time would need to pass for the clock to complete even one round-trip flash. Flip that relationship around, from the clock's own would-be point of view, and the statement usually offered is the tidy one, the one that fits neatly into 90 seconds of narration. At the speed of light, no time passes at all. 0. That is the sentence almost every explanation stops at, but it is not quite what the mathematics says. 0 is a number. It sits on the number line, orderly, well-behaved, available for arithmetic. What the equations governing a light clock's own elapsed time actually produce, when you plug in the speed of light exactly, is not a small, tidy zero sitting patiently at the origin. It's a division by zero, the specific mathematical phrase for a quantity the equations refuse to assign any value to at all, tidy or otherwise. Physicists have a precise word for what that kind of result means, and the word is not zero. The word is undefined. Undefined and zero look similar on a page. They are not remotely the same claim. There's a smaller, everyday version of the same trap. Ask how a cake should be divided among 0 guests, and you won't get back a tiny sliver or even a zero-size sliver. You'll get a question with no valid answer to give at all, because divided among 0 was never a coherent instruction to begin with. That is closer to what undefined means here than any answer built from 0, infinity, or the number 1. Hold that difference for a moment, because everything left to explore tonight lives inside the gap between those two words, between a light clock that ticks 0 times cleanly and a light clock for which the entire concept of ticking, elapsed time, and its own point of view may never have been a coherent question to ask in the first place. Every observer physics has ever described. You, a muon, a proton circling under the Alps, a mirror clock in a train, has one thing in common that goes almost unnoticed. Each of them can, in principle, sit still. Each one has its own valid rest frame, a legitimate point of view from which it isn't moving at all, and everything else in the universe is what's doing the moving. Light does not have that. Every equation in special relativity describing how time, length, and simultaneity change between observers requires, as a basic condition for the math to function, that the observer in question is moving slower than light, not equal to it. Try to construct light's own rest frame, the reference point from which light itself would supposedly measure 0, elapsed time for its own journey, and the equations don't return an answer. They return the word undefined, the same word from the mirror clock, now applied to the entire idea of a photon's point of view. There is no chair for light to sit in, not a difficult chair to reach, not a chair reserved for the extremely fast. No chair at all, anywhere in the mathematics, built for something moving at exactly the speed the rest of the universe measures light to travel. Physicists have a technical name for the kind of path light traces through space and time, a null path. And along a null path, every equation built to measure elapsed time collapses to a single, repeating value. Not a small amount tending toward nothing, but none, built directly into the geometry from the first line of the mathematics, the way a circle's geometry simply does not include corners for anyone to eventually go looking for. It isn't that no one has found light's clock yet, it's that the geometry light moves through was never built with a clock face on it at all. Which leaves the sentence at the center of tonight's question. Light does not experience time, sitting in an uncomfortable place. But it is not, strictly, a measurement anyone has ever taken. It is not, strictly, even a claim the equations are willing to make in ordinary form. It is a limit. The direction every formula points as you approach the speed of light, without ever quite being permitted to arrive. And limits are not nothing, a limit that every equation in modern physics agrees on, unanimously, without exception, for over a century. It says, as clearly as mathematics is able to say anything, whatever is actually true about light's relationship to time, it is not going to be found by asking what light experiences. It is going to be found not in what light experiences, but in what happens to everything else. To causality, to simultaneity, to the very idea of at the same time. Once a universal speed limit with no rest frame of its own is allowed to sit at the center of physics. That is where tonight goes next. Time dilation was never traveling alone. Bolted to it, in the same equations, is a second effect most explanations mention only in passing, if at all: length contraction. As an object's speed climbs toward the speed of light, its length, measured by someone standing still and watching it go by, does not stay fixed. It shrinks in the direction of travel only by exactly the same factor that its onboard clock slows. Push the math to the same extreme used on the mirror clock, and the result is not subtle. A spacecraft capable of reaching 99.99% of light speed would appear, to an observer watching from a planet it passed, compressed to a small fraction of its resting length, nose and tail crushed toward each other along the direction of flight. Though nothing aboard the ship would feel compressed at all, yet to anyone riding inside it, the ship is exactly as long as it always was. The shrinking exists only in the measurement made from outside, the same way the slowed ticking of the mirror clock existed only from outside. This is not a disagreement anyone could resolve by comparing notes more carefully, either. There is no neutral umpire vantage point available anywhere in the universe from which to declare one of the two measurements the real length and the other an illusion. Both are real. Both are correct. They simply belong to different frames. This is not only a hypothetical for spacecraft too fast to build. The muons that fell onto Mount Washington earlier tonight lived a version of the same shrinking. From their own fleeting reference frame, they weren't surviving a 9-mile fall by dilating time at all. The 9 miles of atmosphere above your head simply weren't 9 miles long from where they were falling. The distance itself had contracted to match the little time available to them. Stretched time from the ground, shrunken space from the muon. The same 9-mile survival, told twice in 2 different units, now run both effects to their absolute limit. The one no accelerator has ever reached. The speed of light itself. Time dilation there does not merely grow large, it becomes undefined. As already covered, length contraction, riding the exact same factor, does not merely shrink small, it goes to zero. A photon's length, in its direction of travel, contracted by the same equation that undefined its own clock, would have to vanish entirely. The two properties every ordinary observer relies on, a length to be measured and a duration to measure it in, collapse at precisely the same speed for precisely the same underlying reason, not 2 separate mysteries. One mystery showing up twice in 2 different units. Physicists sometimes describe this by saying a photon's world line. The path an object traces through the combined fabric of space and time has 0 length along it, regardless of how many billions of light years it appears to cross from the outside. Every other world line in the universe, no matter how brief or how still, has some non-zero length to it. A real duration, a clock riding along that path, would actually tick through. A photon's world line is the one documented exception, the single case in all of physics where the length of an entire journey, start to finish, adds up to nothing at all, somewhere between the launch and the arrival. Not for you, not for any observer ever built. There may be no journey to describe at all. In 1917, working to explain his own theory to a non-specialist audience, Einstein offered one of the most quietly destabilizing thought experiments in the history of physics. Not a spacecraft, not a mountain, just a train, a platform, and 2 bolts of lightning. Picture yourself standing on a long station platform while a train moves past at a steady speed. At the exact moment the train's midpoint passes you, lightning strikes both ends of the train at once, genuinely, simultaneously. According to your position, exactly halfway between the 2 strike points, where both flashes of light arrive at the same instant. Now consider a second observer, seated at the midpoint of the train itself, moving along with it. By the time the light from either strike reaches this second observer, the train has carried them slightly closer to one strike point and slightly farther from the other. Light travels at the same fixed speed for both observers. That rule never bends. So the flash from the strike the train is moving toward arrives first, and the flash from the strike the train is moving away from arrives measurably later. 2 observers, 1 pair of lightning strikes, two different, equally correct answers to the question of which one happened first. And neither of them is mistaken, confused, or looking at faulty equipment. Run either observer's stopwatch through a calibration afterward, and it checks out perfectly accurate, perfectly ordinary. The disagreement isn't a flaw hiding in an instrument anywhere. It is a property of the universe both instruments are faithfully reporting on. This is the part you have to sit with a little longer to feel its full weight. It is not a disagreement about when the light arrived. Both observers can agree, down to the nanosecond, on exactly when each flash reached each of their eyes. The disagreement is about something that sounds like it shouldn't be up for debate at all. Which of the two events actually happened first, out in the world, independent of anyone watching? Newton's universe had one answer to that question. The same answer for everyone, everywhere, always. But Einstein's universe does not. Simultaneous turns out not to be a fact about the universe waiting to be measured correctly. It is a fact that depends on how fast the person doing the measuring happens to be moving. Information as relative as left and right, as before and after, depending on which way a room is facing. That claim does not stay small, and it does not stay confined to trains. If two lightning strikes a few hundred feet apart can refuse to agree on their own order because of nothing more than a walking pace of relative motion, the same refusal to agree scales with distance, and it will return tonight in a form strange enough that two people passing each other on an ordinary sidewalk will turn out to disagree about events happening in a galaxy neither of them can see. A Dutch physicist named C. W. Rietdijk took the lightning strike problem from the train platform and pushed it somewhere. Einstein's own illustration never went. Publishing his argument in 1966, he asked what happens to now, once the two observers disagreeing about simultaneity are not sitting a few hundred feet apart, but moving past each other at an ordinary walking pace, anywhere on Earth, with an entire galaxy sitting in the disagreement between them. The physicist, Roger Penrose, would later describe the same argument with a single, vivid image. Picture two people passing each other on an ordinary sidewalk, walking at nothing faster than a brisk human pace in opposite directions. Each of them has a personal plane of simultaneity, their own private answer to the question of what is happening right now, everywhere in the universe. From where they stand, for anything nearby, on the sidewalk, in the city, those two planes agree closely enough that the difference is meaningless. But extend that same plane of simultaneity out to the Andromeda Galaxy, some 2.5 million light-years away, and the tiny difference in walking speed between the two pedestrians becomes an enormous difference in which events on Andromeda count as already happened. From each person's point of view, the math is not exotic. At ordinary walking speed, the two pedestrians' respective right now on Andromeda can differ by several days. One of them, according to the physics both are equally subject to, is living in a present moment that includes events the other pedestrian's present moment has not reached yet. Neither pedestrian is wrong, neither reference frame gets to overrule the other. And if both of their nows are equally valid descriptions of a single galaxy far away, the argument Rietdijk built and Hilary Putnam independently reached a year later follows almost unavoidably. Whatever is already decided in one valid present moment must, in some sense, already exist, even if it hasn't been reached yet by a slower-moving observer's version of now. Stretch that same argument from a distant galaxy back to an ordinary human life, and the implication stops being abstract. If simultaneity is in fact this relative, there exist valid, physically legitimate reference frames, moving fast enough, far enough away, for which events in what feels, from here, like an unarrived future, have already taken their place in the same block of space-time as everything that has already happened. Not predicted, not probable, already there in the structure itself for someone else's version of now. Physicists call this interpretation the block universe. Past, present, and future, all equally real, equally fixed, differing only in which slice of the block a given observer's now happens to be cutting through. None of this has been resolved into comfort. Whether the block universe is the correct way to read the mathematics, or merely one permitted way among several, remains genuinely contested among physicists who agree on every equation and disagree entirely on what the equations are describing. But if it is correct, then somewhere in the same four-dimensional structure that already contains everything you have ever done, your next decade is not waiting to be written. It is already sitting there, finished, for a version of now that simply hasn't reached you yet. In October of 1971, a physicist named Joseph Hafele and an astronomer named Rietdijk carried 4 cesium beam atomic clocks onto a series of ordinary commercial airline flights and set out to do something almost absurd in its simplicity: fly around the world twice in opposite directions and see whether time itself came back different. The prediction they were testing combined 2 effects working in opposite directions. Special relativity, said the clocks, moving at the plane's ordinary cruising speed relative to a reference clock left behind at the United States Naval Observatory, should run slightly slow. The same effect already measured on Mount Washington, just far gentler, since airliners move nowhere near the speed of the muons falling through the atmosphere. But general relativity added a second, competing effect. Clocks farther from the Earth's mass, at cruising altitude, run very slightly fast, because gravity itself slows time nearer to a large mass, and being 30,000 feet up means being just slightly less gravitationally slowed than sitting on the ground. Flying eastward, with the plane's ground speed adding to the Earth's own rotation, the velocity effect was expected to dominate, predicting the airborne clocks would fall behind the ground clock by a small number of billionths of a second. Flying westward, against the Earth's rotation, the calculation flipped, predicting the airborne clocks would instead pull ahead. When Hafele and Keating compared their flown clocks to the reference clock back in Washington, the eastbound clocks had lost close to 60 billionths of a second. The westbound clocks had gained close to 270 billionths of a second. Both numbers, in both directions, landed within the margin of error of what Einstein's equations. Not one equation, but the combined predictions of 2 separate theories from 2 separate decades of his career had said they would. 60 billionths of a second is not a number that changes anyone's flight schedule, but it is a number that took 2 working theories about the nature of gravity and motion, applied them to ordinary airline tickets, and returned an answer precise enough to confirm both at once, in public, with commercially available airplanes, and a set of atomic clocks that needed their own paid seat. A boarding pass bought for a suitcase full of cesium and electronics, buckled in like any other passenger. You have likely flown on a plane at some point in your life, crossing time zones without a second thought for the atomic clocks, disagreeing with the ground beneath you by a few billionths of a second the entire flight. The disagreement is real. It is simply too small, at ordinary cruising speed, for any nervous system to notice. The same billionths of a second Mount Washington's muons spend their entire short lives living inside. Time is not a backdrop the rest of physics happens in front of. It is a quantity, one that can be loaded onto a plane, flown around a planet, and unloaded again measurably changed. When the first GPS satellites were designed in the 1970s, the engineering team building the system faced a decision that had nothing to do with rockets or radios, whether to believe Einstein. The satellites would orbit at roughly 12,000 miles up, moving fast enough for special relativity to slow their onboard clocks by about 7 microseconds a day, and sitting far enough from Earth's mass for general relativity to speed those same clocks up by about 45 microseconds a day. Combined, the prediction was that an uncorrected satellite clock would run fast by approximately 38 microseconds every single day. A number confirmed, independently, by nothing more exotic than airline atomic clocks a few years earlier. Some of the engineers did not fully trust it. Relativity was, to them, still an abstraction proven in laboratories and mountaintop particle detectors, not something they were eager to bet an entire navigation system on without a safety net, especially one that every future ambulance, airliner, and stranded hiker would eventually come to depend on without ever knowing it. So the very first GPS satellite launched with a built-in option, a switch that could enable or disable the relativistic correction to its clock in case Einstein turned out to be wrong at orbital altitude, a contingency plan for a possibility almost nobody involved actually expected to need. But the switch was left off at first, so the ground team could measure the drift directly rather than trust the math alone. The clock drifted. It drifted at almost exactly 38 microseconds a day, matching the prediction closely enough to end the argument. The correction was switched on. It has stayed on, quietly, in every GPS satellite launched since, adjusting each atomic clock's tick rate before it ever reaches orbit so that it will run at the correct pace once relativity finishes doing its work on the way up. No later satellite generation has ever needed to seriously revisit the decision. The number has held steady, launch after launch, decade after decade, exactly as predicted the very first time anyone bothered to check, on hardware built by engineers who mostly just wanted the maps to be right. None of the engineers who flipped that switch in the 1970s could have known how far the consequences would travel. Into phones not yet designed, into cars not yet built, into an entire economy of location-dependent apps that would one day depend, every second, on a correction for a photon's undefined clock without a single user ever learning why. Now, follow what an uncorrected clock would actually do, because the chain from there is not abstract at all. 38 microseconds a day sounds small. Multiplied by the speed of light, though, a timing error of 38 microseconds becomes a positioning error of roughly 7 miles. Every single day, compounding, never resetting itself. Emergency dispatchers routing an ambulance would be working from a map that drifts by city blocks within a week. Aircraft navigation, container ship routing, the timestamps banks use to sequence financial transactions down to the millisecond. All of it depends on a correction built to patch a disagreement about time that begins with a photon's undefined clock and ends, 100 years later, in a chip inside your pocket, in your hand, right now. Not every physicist accepts the block universe as the correct way to read what relativity is saying, and the disagreement is not a fringe one. You are, in all likelihood, a presentist by instinct, certain, without ever having to argue for it, that only right now is real, that the past is simply gone and the future simply hasn't happened yet. Physics has never been able to fully confirm that instinct, and relativity, if one entire camp of physicists is correct, forbids it outright. One camp, sometimes called eternalists, takes the mathematics at face value. If relativity of simultaneity means different observers legitimately disagree about which events are already real, then reality itself must include all of it at once, past and future alike, with the sensation of time flowing, reduced to a side effect of consciousness moving through an already complete structure. The way a reader's eye moves through a novel whose ending was printed before you ever opened the first page. A second camp rejects that conclusion, not because the equations are wrong, but because the equations, in this view, were never built to answer the question in the first place. Time may still genuinely flow, one moment at a time actually real, and relativity's disagreements about simultaneity would then be describing something about measurement and observation, not the deeper, unmeasured fact of which single moment is currently happening. Physicists in this camp, including some working on the foundations of quantum gravity, argue that a complete theory of physics has not yet been found, and that when it is, it may restore a single, universal, now that relativity's simpler mathematics was never equipped to see. Both camps agree completely on every experimental result covered tonight: the muons, the airline clocks, the GPS correction, They diverge only on what those results mean about the nature of reality itself, and neither side has produced an experiment capable of settling it. The stakes are not only academic. If eternalism is correct, every version of every person who has ever lived remains, in some sense, still there. Not remembered, not gone, but genuinely present, somewhere else in the same structure that contains this exact moment. If presentism is correct instead, that comfort dissolves the instant it's offered. Only now is real, and everything else, including every person no longer living, has simply stopped existing at all. But physics, remarkably, does not currently have the authority to say which of those two very different universes anyone actually lives inside. This is not a gap waiting for better instruments. It may be a gap physics is not currently built to close, because the disagreement lives one level beneath anything a clock, however precise, is able to measure. Tonight will not resolve which camp is right. We are going to sit inside that disagreement instead, unresolved, because it may be the truest thing this whole night has to offer. Not an answer, but the exact shape of a question physics has not yet learned how to close. Every disagreement about which happened first described so far tonight has one quiet requirement hiding inside it. It only applies to pairs of events that could never have influenced each other in the first place. Physicists draw this boundary using a shape called a light cone, an expanding sphere of everything light could reach, radiating outward from any single event in every direction at once. Everything inside that expanding sphere is causally connected to the event at its center. Light, or anything slower, has time to carry an influence there. Everything outside it, at that same moment, is causally disconnected. No signal, no force, no cause of any kind, moving at any speed the universe permits, could possibly get from one to the other in time. The lightning strikes on Einstein's train were outside each other's light cones relative to the timescales involved. Neither strike could have caused the other. So different observers were free to disagree about their order without breaking anything. The same is true of Rietdijk's distant galaxy. Events on Andromeda and a pedestrian's afternoon walk are so remote from each other, causally, that disagreeing about their order cost the universe nothing at all. There was never a ripple connecting the two of them to begin with, but bring two events inside each other's light cones, a struck match and the flame that follows it, a signal sent and a signal received. And the disagreement vanishes completely. Every observer, moving at any speed whatsoever, in any direction, agrees on which one came first. Cause always precedes effect. For absolutely everyone, without a single documented exception in over a century of testing, the universe permits enormous, vertiginous disagreement about simultaneity in the one region where it costs nothing and enforces perfect, universal agreement in the one region where getting it wrong would unravel everything else. Return, for a moment, to Betelgeuse from the very start of tonight. Whatever that star is doing right now sits outside your light cone entirely, which is precisely why observers moving at different speeds are free to disagree about its current state without the universe so much as blinking. But the moment its light finally reaches Earth, centuries or millennia from now, the situation changes completely. That arrival becomes an event inside a shared light cone, and every observer, however fast or slow, will agree completely on the fact that it happened, and on everything that led up to it. That is not a coincidence, and it is not a patch bolted onto relativity after the fact to keep the theory respectable. It is the same underlying structure, doing both jobs with a single rule. Nothing, in any circumstance discovered so far, outraces light. Your own life, right now, sits at the exact center of one of these expanding light cones, quietly dividing the entire universe into everything that could ever possibly affect you, and everything that, no matter how carefully it's measured, from any reference frame at all, by any observer who has ever existed simply cannot. You have likely heard the phrase spooky action at a distance at some point without ever learning why physicists still argue about what it means. Nearly everything covered tonight agrees on a single boundary. Nothing outraces light. There is exactly one experimentally confirmed phenomenon in modern physics that still makes that boundary look, at first glance, like it might have an exception. And even now, decades after the experiments were first run, physicists have not fully agreed on how to talk about what is actually happening. Quantum entanglement links two particles so that measuring a property of one instantly correlates with the outcome of measuring the same property on the other, regardless of the distance between them. A laboratory result confirmed repeatedly, including with particles separated by hundreds of miles with no detectable delay between the two measurements, no matter how carefully the timing is checked. For decades, this troubled physicists enough that it earned its own name, borrowed from an objection Einstein himself raised: spooky action at a distance. If measuring one particle instantly affects what the other one does, and the two are far enough apart that light itself couldn't have carried a signal between them in time, something appears to be moving faster than the speed limit that governs everything else in this episode. Picture two detectors in separate laboratories, each measuring the polarization of one particle from an entangled pair. Neither detector, on its own, ever shows anything but an unpredictable string of results. Sometimes one orientation, sometimes the other, with no pattern either lab could detect alone. Only when the two logs are carried to a common location afterward and compared side by side does the impossible-looking correlation reveal itself. Results that should have been independent turn out to have matched the entire time, as if you had been comparing notes with your own reflection in a mirror on the far side of the galaxy. Experiments testing exactly this setup have been run repeatedly since the 1970s, with the distance between the two detectors steadily increased over the decades. From a single laboratory bench to separate buildings, then separate cities, then, more recently, ground stations linked through an orbiting satellite hundreds of miles overhead. The correlation has never once weakened, faded, or shown any sign of a delay creeping in as the distance grew. Here is where the boundary reasserts itself, in a form stranger than a simple exception. The correlation between the two particles is real and instantaneous, but no usable information can be sent by it. No message a person at one end could use to influence a choice made by anyone at the other end faster than light would otherwise allow. The outcome of each individual measurement looks, on its own, like pure randomness. Only when the two lists of results are later compared, brought back together by an ordinary, light-speed limited exchange of information, does the correlation between them become visible at all. So the speed limit survives, technically, by the narrowest possible margin. Something connects the two particles across any distance, instantly, in a way physicists can measure and rely on. And yet nothing about that connection can be used to send so much as a single bit of a message faster than light allows. What that something actually is, a real physical influence, a deeper structure connecting the particles that was never truly separate to begin with, or something language does not yet have the right words for, remains one of the most contested open questions in physics. Tonight will not settle it. It may be settled within a few years by an experiment not yet designed, or it may still be sitting exactly here in another 100 years, unresolved, the same way it is tonight. Every equation used so far tonight, the light clock, the Lorentz factor, even the light cone itself, works exactly the same if time is run backward. Physicists call this time reversal symmetry, and at the level of individual particles and forces, it is nearly universal. A video of two atoms colliding, played in reverse, depicts a scene that violates no fundamental law of physics whatsoever, and yet nothing about lived experience feels remotely reversible. Glasses shatter and do not reassemble. Coffee cools in a room and never spontaneously boils by drawing heat back out of the air. People remember the past and never the future. Somewhere between the reversible mathematics of individual particles and the irreversible experience of an entire life, an arrow appears, pointing one direction and one direction only, and nothing in the basic equations explains where it came from. The leading explanation involves a quantity called entropy, roughly a measure of how many different ways the microscopic pieces of a system can be arranged while still looking the same from the outside. An unbroken glass has very few such arrangements. Shattered glass scattered across a floor has an almost uncountable number of them. The second law of thermodynamics states that entropy in any closed system only ever increases, never decreases, which is why the glass shatters and stays shattered, why the coffee cools and stays cool, why memory only ever accumulates in one direction. A useful way to feel the difference. Shuffle a brand new, perfectly ordered deck of cards for 30 seconds, and it becomes disordered. Shuffle a disordered deck for 30 seconds, and it does not spontaneously sort itself back into suits and sequence. Not because doing so is forbidden, technically, but because the number of disordered arrangements so vastly outnumbers the handful of ordered ones that landing back on order by chance would take far longer than the current age of the universe, repeated many times over. But the second law does not explain why the universe started in a state of low entropy in the first place. The one condition required for entropy to have anywhere to increase from, nothing in the fundamental equations forbids a universe that began in maximum disorder and has been getting steadily tidier ever since. Glasses unshattering, coffee spontaneously warming, memories running the wrong way. That universe would break no law of physics tonight has described. It simply is not the universe anyone has ever measured. So the arrow of time that makes before and after feel like the most obvious facts in existence turns out to rest on a single, unexplained starting condition, a coincidence of the universe's earliest moment that nothing in the mathematics required and nothing in the mathematics has yet explained. You will fall asleep at some point tonight without ever worrying that you might wake up younger than you went to bed. That confidence is not guaranteed by any law of physics named so far. It is borrowed entirely from a low entropy starting condition set at the very beginning of everything. One this entire universe has been spending, unable to stop, ever since. Every thread followed so far tonight keeps arriving at the same locked door from a different direction. The muons on the mountain, the accelerator under the Alps, the mirror clock pushed to its limit. All of it converged on a single mathematical fact. Light's own relationship to time is not measurable, not zero, but undefined, a limit no experiment can approach. The train platform, the pedestrians unknowingly disagreeing about Andromeda, the block universe some physicists take seriously and others reject outright. All of it converged on a second fact. Now is not one thing, shared identically by everyone, but a private slice through a four-dimensional structure that different observers cut at different angles. And running underneath both of those facts, still unexplained, sits a third, the arrow pointing from past to future, the one that makes memory run backward and forgetting run forward, resting on a starting condition nobody has been able to account for. 3 separate investigations, one unanswered question, showing up in 3 different disguises. What is time, actually? Not as a number on a clock face, but as whatever it is that a photon does not have, that now cannot universally agree on, and that somehow still insists on flowing in only one direction for every person who has ever lived. You have never once seen the present moment shared in the way it always felt like it should be shared with anything you were looking at. The star overhead, the stranger across the room, even once light has to cross the small gap between a page and an eye, this very sentence. But none of these 3 mysteries cancelled the other 2 out. They stacked. A century of increasingly precise instruments did not simplify the picture of time. It complicated it in 3 separate directions at once, and every new experiment since has only added weight to all 3 columns simultaneously, never subtracting from any of them. None of it happened quickly. and none of it happened by accident. Physics has spent more than a century getting extraordinarily precise about how all of this works. It has landed atomic clocks on airplanes, corrected billions of satellite calculations a day, and confirmed the same startling equations from a mountain in New Hampshire to a tunnel outside Geneva. None of that precision has been wasted. GPS satellites, particle accelerators, and airline schedules all quietly depend on getting it exactly right every day without incident. What it has not done, what nothing covered tonight has done, is explain what time actually is underneath all of that behavior, well enough for every physicist to agree. That gap is where the rest of tonight goes looking. Into places stranger than a mountain in New Hampshire or a tunnel outside Geneva, into questions physicists have not agreed to stop arguing about, and into at least one idea that will make even the word now feel considerably less solid than it seemed when tonight began. Two physicists, Bryce DeWitt and John Wheeler, once wrote down an equation meant to describe the wave function of the entire universe at once. Not a planet, not a particle, everything. All matter and all geometry, folded into a single mathematical object. Published in 1967, it remains one of the most ambitious equations ever proposed in physics. Neither man had any way of knowing it would still be unresolved when you were born, let alone now. It also, notoriously, and to the visible discomfort of several generations of physicists since, contains no variable for time. Every other major equation in physics, the one governing a single electron, the one governing a swinging pendulum, even the equations behind the mirror clock earlier tonight, has a place where time explicitly enters, a term that says how the system changes from one moment to the next. But the Wheeler-DeWitt equation, describing the entire universe at once, has no such term. Solve it, and what comes out the other side is a description of the universe that does not, in any of the usual mathematical sense, evolve. None of this means your kitchen clock is secretly malfunctioning, or that physicists have given up on describing change. At the scale of a kitchen, a heartbeat, or a falling apple, ordinary time works exactly as expected, and no experiment has ever caught it failing. The absence of time shows up only at the largest scale anyone has ever tried to describe mathematically. The whole universe, considered as a single quantum object, and nowhere smaller than that. Physicists have argued for more than 50 years about what this actually means, and the argument shows no sign of quieting down. Some treat it as an artifact of an incomplete theory, a placeholder waiting for the correct combination of quantum mechanics and gravity to restore time to its rightful place. Others take it as something closer to a genuine discovery. Perhaps the deepest layer of reality is in fact a single, frozen, timeless structure, and everything that feels like change, motion, or the passage of a single second is something added on top of that structure by whatever is doing the observing. Not fundamental, but assembled. Neither camp has been able to force the other's hand experimentally in more than 5 decades of trying. Careers have been built and finished on both sides of the disagreement without a single crucial experiment arriving to settle it. Tonight's central mystery just found its widest possible aperture. A photon's clock is undefined. The order of distant events depends on the observer. Entropy provides a direction, but not an origin. And now, at the deepest layer physicists have ever attempted to write mathematics for, the very variable every earlier disagreement was actually about time itself. May not appear in the fundamental description of reality at all. A description that, if the timeless camp turns out to be right, includes you. Reading this sentence as a single, unmoving thread in something that was never flowing to begin with. Physicists Don Page and William Wouters once proposed a way to make peace with a timeless universe, publishing the idea in 1983. Perhaps time was never a property of the whole system to begin with, but something that only appears once you split that system into 2 entangled halves. A clock piece and everything else piece, and ask what the everything else piece looks like from the clock's point of view. Their idea, sometimes called the Page-Wouters mechanism, works like this. Even if the universe as a whole has no time variable, evolving nowhere, a smaller piece of it, a subsystem playing the role of a clock, can become entangled with the rest. Correlations between the clock's readings and the state of everything else would then create the appearance of change, from the inside, purely through those correlations, even while the total system, viewed from outside, does nothing at all. Nobody expected this idea to be testable with equipment that fits on a lab bench. But in 2013, a team of physicists, led by Ekaterina Moreva, built a small toy version of exactly this setup using pairs of entangled photons, treating one photon as a stand-in clock and the other as a stand-in universe. Measured together, the photons behaved as if time were passing. Measured in a way that excluded the clock photon's information, the system showed no change whatsoever. A miniature, laboratory-scale echo of a universe that might have no time in it at all, except from the inside of one of its own entangled parts. A small photon standing in for every clock, every heartbeat, every observer that has ever existed. You are, in this proposal, exactly that kind of entangled subsystem. A clock made of neurons and heartbeat, correlated with the rest of the universe closely enough to feel time passing, even if the larger structure containing you does nothing of the kind. The appeal of the idea is that it does not require abandoning either theory to make peace with the other. General relativity keeps its flexible, observer-dependent time. Quantum mechanics keeps its entangled, correlation-based description. Neither one has to be wrong for the picture to work. They simply have to be describing two different scales of the same structure, one from outside a system that has no time, and one from inside a piece of it that, through entanglement alone, behaves as though it does. Whether that is a genuine resolution or an elegant reframing that avoids the hardest part of the original question remains, itself, an open argument among the physicists working on it. None of this proves time is an illusion in any everyday sense. It has not stopped a single clock from ticking, a single heart from beating, a single flight from landing on schedule, but it suggests something stranger than illusion or reality, that time might not be a stage the universe performs on, but a relationship, something that exists only between one part of the universe and another, never in the whole at once. Two of the most successful theories in the history of physics, general relativity and quantum mechanics, have never been fully reconciled. And the reason is not a missing equation or a stubborn calculation. The reason is that they disagree at the most basic level about what time is even for, a disagreement neither theory's supporters have ever managed to talk the other out of. In quantum mechanics, time is a fixed background parameter, a steady stage every particle and wave performs on, external to the system and never itself affected by what happens on it. In general relativity, time is not a stage at all. It is part of the performance, woven into the same flexible fabric as space, stretched and compressed by mass and speed. Different for every observer depending on where they stand and how fast they move. Try to build a single theory that uses both descriptions at once, and the two notions of time refuse to sit in the same equation peacefully. But quantum mechanics needs a fixed clock outside the system to make sense of its own mathematics, and general relativity insists no such fixed, universal clock exists or can exist anywhere. Every serious attempt at a theory of quantum gravity, the sought-after framework that would finally unite them, runs headlong into this same disagreement before it gets anywhere near a testable prediction. Decades of careers, entire research institutes, and generations of graduate students have been devoted to finding a way around it, with no consensus solution yet in hand. Neither side has budged in decades. The two leading research programs trying to close this gap do not even agree on the shape of the solution. String theory tends to keep something resembling quantum mechanics' fixed background and try to fit gravity into it. Loop quantum gravity does the opposite, starting from relativity's flexible, background-free geometry and trying to make quantum mechanics fit inside that instead. Decades of work from thousands of physicists have produced elegant mathematics on both sides, and no experiment yet capable of telling either community which starting point, if either, is the right one. Physicists sometimes call this the problem of time, and it is not considered a minor technical snag. It is treated, by many researchers working on it, as evidence that neither theory's picture of time can be the final one, that something more fundamental is still missing, a description in which both the quantum world's fixed clock and relativity's flexible fabric turn out to be approximations of a single, deeper structure nobody has yet written down. Every attempt at a solution runs into the same wall from a slightly different angle. Some approaches try to quantize gravity directly, treating space-time itself as made of discrete, countable pieces at the smallest possible scale, small enough that the very idea of a smooth, continuous time might stop applying at all. Others try to derive gravity as an emergent effect of ordinary quantum information, with time appearing only as a byproduct of that emergence rather than a starting ingredient. Neither approach has produced a single confirmed prediction distinguishing it from its rivals after decades of some of the most sophisticated mathematics ever developed by any branch of physics. You have been living your entire life inside both descriptions simultaneously, without ever noticing the seam between them. Every clock you have ever read has run on relativity's flexible time. Every particle inside your body has behaved, moment to moment, according to quantum mechanics' fixed time. The two have never once been caught contradicting each other in any experiment ever performed, and no one has ever fully explained why not. In the 1990s, mathematician Alain Connes and physicist Carlo Rovelli proposed an idea stranger than anything covered so far tonight: that time itself might not be fundamental at all, but a byproduct of incomplete information. Specifically, of the fact that no real observer, anywhere, can ever track every microscopic detail of the system they're part of. Their proposal, called the thermal time hypothesis, is one of the more quietly radical ideas in modern theoretical physics, and it starts from an old idea in thermodynamics. Temperature and the flow of heat only make sense once you accept that you cannot track every individual particle in a gas, only broad statistical patterns across billions of them. Connes and Rovelli extended that same logic to time itself. In a description of physics with no built-in time variable, the same kind of timeless structure the Wheeler-DeWitt equation hints at. An observer who can only access partial information about the whole system will still perceive something that behaves exactly like the flow of time, generated purely by the statistics of what that observer cannot see. On this view, a being capable of tracking every last detail of the universe, missing nothing, would perceive no time passing at all, not because time would be moving too fast or too slow for them, but because time, for a complete and total observer, may not be a meaningful concept in the first place. Time, in this picture, is not woven into the fabric of reality. It is something reality produces for anyone forced to look at it through a keyhole instead of the whole room. Picture standing in a large, dim room, able to see only a single keyhole's worth of it at a time. Someone with the full room in view all at once might report that nothing in the room is moving. The furniture, the light, all of it simply existing in one arrangement. Someone limited to the keyhole, catching only fragments in sequence, would swear the room is constantly changing, full of motion and passing moments. Both would be looking at the same room. Only one of them would be experiencing anything like time. This connects, uncomfortably, to the arrow of time from earlier tonight, the entropy that only ever increases, the glass that shatters and stays shattered. If Connes and Rovelli are right, That arrow and the very sensation of time passing at all might be two faces of the same underlying fact, that no observer inside the universe, including every observer who has ever lived, gets to see the whole picture at once. You are, by this account, not failing to perceive time correctly. You are perceiving it exactly the way anything limited to a partial view of reality would have to. But the hypothesis remains exactly that. A hypothesis, mathematically serious. Taken seriously by researchers working on the foundations of quantum gravity, and nowhere near confirmed by an experiment capable of telling it apart from its several competitors, thermal or otherwise. What makes it worth sitting with, even unconfirmed, is how naturally it would explain something no other proposal tonight quite manages. Why time feels the same to every limited observer, everywhere, despite none of them ever agreeing on much else. Strip away every specific proposal covered so far tonight. The timeless master equation, the entangled clock, the keyhole observer, and one plain, unresolved question remains underneath all of them. Is time fundamental? A basic ingredient of reality that cannot be broken down any further? Or is it emergent, something assembled out of deeper, more basic pieces? The way temperature is assembled out of the motion of countless individual particles, invisible until enough of them are counted at once? Physicists are not merely undecided the way a jury might be undecided before enough evidence arrives, waiting patiently for a verdict everyone expects to eventually arrive. They are working, right now, in parallel, on frameworks built on each assumption, publishing results, training students, building entire careers on both sides of a question neither side can currently test against the other. Some argue time must be fundamental, because every attempt to build it out of something else has produced mathematics too strange, too far removed from anything resembling ordinary experience to be trusted without direct evidence. Others argue exactly the opposite, that the deepest lesson of the last 100 years of physics, general relativity dissolving absolute space, quantum mechanics dissolving definite properties before measurement, has been a steady erosion of things once assumed basic, and that time is very likely next. Neither side considers the other naive. Physicists arguing for a fundamental time can point to a century of theories that tried to explain it away and failed to produce a single confirmed prediction. But physicists arguing for an emergent time can point to an equally long list of things. Absolute space, a universal present, the sharp line between particle and wave, that seemed just as fundamental, right up until the moment better mathematics dissolved them. Both lists are real, and both keep growing. Neither one settles which pattern time will end up following. Tonight will not settle which side is correct, and no one currently working in the field expects it to be settled soon. Not because the question is unimportant, because it may be the single most important open question in physics. And important questions, historically, have taken generations to answer. When they get answered at all, time may be the last shore physics has not yet mapped. Not because no one has sailed toward it, but because every ship that tries seems to change the shape of the water as it approaches. You have spent this entire episode assuming, reasonably, that time is simply there. A given, not a question. Tonight has not taken that assumption away. It has only shown you the size of the crack running underneath it. A crack every physicist currently alive is still trying to measure. A photon does not experience time. Whether time, in the end, is something anything experiences at all. Fundamentally, rather than as a trick played on limited observers, is a question this entire night has been circling without ever fully landing on. Every unresolved question from the last several minutes. Whether time is fundamental or built from something else, whether the whole universe secretly has no time variable at all, whether an observer's limited view is somehow the true source of time's flow, shares one thing in common. None of them can be tested directly. Each is a serious, mathematically grounded proposal argued by serious people, and each remains, for now, a story consistent with the equations, rather than a fact confirmed by them. There is exactly one place, in all of tonight's journey through the nature of time, where the mathematics does not merely propose something about time. It simply states it, flatly, without competing schools of thought, without a hypothesis still waiting for its experiment. A photon's own relationship to time is undefined, not because physicists lack the tools to measure it, but because the structure of space-time itself was built without a slot for the question to occupy, held up against the size of everything else covered tonight. Relative simultaneity, the block universe, the timeless master equation, the entangled clock. That one settled fact starts to look less like a strange footnote about a single kind of particle, and more like the plainest hint physics has offered about what all of the unsettled questions are actually asking. Every open question tonight has been a question about how to add time back into a description that keeps losing it, how to recover a universal now, how to explain an arrow pointing one direction, how to make a timeless master equation produce something that feels like change. Light never needed any of that machinery in the first place. It is the one part of this entire universe for which the question of adding time back in simply never comes up, because nothing about its own description was ever built expecting an answer, not why doesn't light experience time. That framing assumes time is the default, and light is the strange exception needing explanation. But run the logic the other direction instead. What if light, undefined, unbothered, existing along a path with no ticking clock built into it at all, is the simplest case in the entire universe, and everything else, every ordinary clock, every heartbeat, every falling asleep and waking up, is the complicated exception that still needs explaining. This is, in the end, a version of the question in tonight's title. How can light travel if it doesn't experience time? As though the strangeness belongs entirely to light. Turn the question back for a moment. You experience time constantly, effortlessly, without ever needing an explanation for why. Physics, after tonight, owes an account of why that is. Why you get that experience and light does not. And it does not yet have a complete one to give. That reframing does not resolve anything covered tonight, but it changes, permanently, which side of the question feels like it needs defending. Take everything covered so far about clocks running slow and push it into the most famous version of the puzzle. Send one twin on a spacecraft toward a distant star at a large fraction of the speed of light, turn the spacecraft around, and bring that twin home. Compare the two afterward, and the traveling twin has aged years, sometimes decades, less than the twin who stayed on Earth the entire time. The puzzle hiding inside this scenario troubled physicists for years after Einstein published Special Relativity, because relativity itself insists that motion is always relative. From the traveling twin's own point of view, it was Earth that flew away and came back, not the spacecraft. If motion is symmetric, shouldn't each twin see the other as the one who aged less? Shouldn't the paradox cancel itself out, leaving both twins the same age when they meet again? It doesn't. And the reason reveals something that easily gets lost in a story about mirror clocks and muons. The two twins are not in symmetric situations, even though their relative motion looks symmetric from a glance. The twin who stays on Earth remains in a single, unchanging, inertial frame for the entire trip. The traveling twin does not. Turning the spacecraft around to come home requires acceleration, a period of actively changing speed and direction, breaking the smooth, unaccelerated motion that would otherwise have made the two situations identical. That acceleration is not a footnote, it is the entire resolution. The twin who feels the push of turning around is the twin whose clock, provably, measurably, ends up behind. This has been tested, in miniature, without ever needing a spacecraft. Commercial jets carrying atomic clocks circling the planet and returning to their starting point, play the role of the travelling twin in miniature, and the clocks that made the round trip come home reading a different number than the one left behind. The same experiment already covered tonight. Wearing the twin paradox's name, none of this makes the travelling twins' experience any less real to them. Their heart beat the usual number of times per minute. Their thoughts moved at the usual pace. Nothing on board ever felt slow, sped up, or strange from the inside. Two people, identical at launch, reunited, having lived through measurably different amounts of time. And both of their experiences, the whole way through, were completely, unremarkably ordinary. You will never fly close enough to light speed to notice this in your own lifetime, but the underlying rule was already running. Quietly, in a jet carrying a suitcase full of cesium, decades before this sentence existed to describe it. Where light fits into this story is where it gets interesting again. Push the travelling twin's speed all the way to light speed itself. Impossible for anything with mass, but useful as a limit, and the gap between the two twins stops being a gap of years. It becomes the same undefined gap discussed earlier tonight. The same gap between the muons borrowed 9 miles and light's borrowed nothing at all. The twin paradox and light's undefined clock are not two separate stories. They are the same story, run out to two different distances along the same scale. Everything covered tonight about time dilation has come from motion. How fast something moves relative to something else. There is a second, completely different way to slow a clock down. One that has nothing to do with speed at all. Simply move it closer to something massive. General relativity predicts that clocks run slower the deeper they sit inside a gravitational field. Not because gravity somehow reaches out and grabs the clock's gears, but because mass curves the structure of space-time itself, and time runs at a different rate, depending on how curved that structure is at a given point. A clock at the base of a mountain, closer to Earth's mass, ticks very slightly slower than an identical clock at the summit. In 1959, two physicists, Robert Pound and Glenn Rebka, tested this prediction using nothing more exotic than a tower at Harvard University, 74 feet tall and a beam of gamma rays sent from the bottom to the top. General relativity predicted the light climbing away from Earth's mass would lose a tiny, precise amount of energy in the process, stretching to a slightly longer wavelength, an effect called gravitational redshift. 74 feet is barely more than the height of a house stacked several stories high, and the predicted effect was smaller than anything anyone had measured before. But none of this required imagining a black hole to become real. Pound and Rebka measured the shift anyway, using a technique sensitive enough to catch a change in energy of a few parts in 100 quadrillion. And the gamma rays behaved exactly as general relativity predicted, redshifted by precisely the tiny amount the equations demanded. In a building that still stands on a university campus today, the precision required to catch an effect that small, in 1959, using nothing more advanced than a laboratory tower and a gamma ray source, remains one of the most quietly impressive measurements in the history of experimental physics. A confirmation of general relativity that arrived decades before satellites, decades before atomic clocks flew on airplanes, using equipment that could fit inside a single university building. This is the same effect, at a gentler scale, that lets a GPS satellite's clock run fast at orbital altitude, even while its speed is simultaneously making it run slow. Two competing predictions, both confirmed, both required to correctly calculate the 38 microseconds discussed earlier tonight. Speed slows a clock down. Distance from mass speeds one up. Every clock you have ever owned has been running at a slightly different rate than a clock down the street, in a different building, at a different elevation. A difference too small to notice, but never too small to be real, near an object massive and dense enough, a neutron star, or the edge of a black hole. This same gentle effect stops being gentle at all. Time dilates enough near a black hole's boundary that, from far away, An object falling in appears to slow down and freeze at the edge forever, its light stretching to redder and redder wavelengths, fading rather than ever visibly crossing the line. Whether anything actually crosses that line, from its own falling point of view, or whether the boundary itself behaves like another version of tonight's undefined nothing, remains one of the most actively studied problems in modern gravitational physics. You are, at this moment, aging very slightly faster than someone lying on the ground floor of the same building, and very slightly slower than someone flying overhead in an airplane. Not by an amount either of you could ever notice, but by an amount every atomic clock on the planet has already confirmed over and over, without exception. Somewhere on Earth right now lives a man who, according to the same physics covered all night, has technically travelled slightly into his own future, not through any device built for the purpose, but simply by orbiting the planet fast enough, for long enough. Sergei Krikalev, a Russian cosmonaut, spent a cumulative total of more than 800 days aboard orbiting spacecraft across several missions in the 1980s, 90s, and 2000s, circling Earth at roughly 17,500 miles an hour the entire time. At that speed, the same time dilation that slowed the muons on Mount Washington and the clocks on Hafele-Keating's airplanes applies to a human body in orbit, gently, in this case, but measurably, and for long enough to add up to something real. By the time he returned to Earth for the final time, Krikalev had aged approximately 0.02 seconds less than he would have if he had simply stayed on the ground the entire time his colleagues were orbiting without him. 20 milliseconds. Not enough to notice in a mirror, or in a conversation, or in anything a human nervous system could perceive directly, but real, calculated from the same equations governing everything covered tonight, and confirmed by the same kind of atomic clock precision that confirmed the muons, the airplanes, and the satellites. 20 milliseconds sounds almost like a joke next to a photon's undefined nothing, or a proton circling under the Alps at 7,000 times slowed. But the direction of the effect is identical, the mechanism is identical, and the only real difference is how much of the fixed cosmic allowance was spent. Krikalev spent slightly more of his on space than the rest of us do, lying still on the ground. Not much more, but measurably more, in the same units, following the same single rule that governs everything, from a mountaintop muon to the light crossing this room right now. He is currently, by strict technical accounting, the closest thing to a confirmed human time traveler this species has ever produced. And the trip cost him nothing stranger than doing his job, extremely well, in orbit, for a very long time. None of this required a spacecraft capable of anything close to light speed. It required patience, a good clock, and 800 days spent doing exactly what physics already predicted would happen. Proof, on a human scale, of the same trade between space and time everything else tonight has already been making. You will never orbit fast enough, for long enough, to notice this in your own body. But the same rule that moved Krikalev 20 milliseconds into his own future has been quietly nudging every person who has ever flown on an airplane, ridden in a fast car, or simply lived at a different elevation than someone else. Smaller nudges, immeasurable by any means available to a human life, but never once absent, never once switched off. 20 milliseconds is not a large number, but it is the same kind of number as 38 microseconds, and 9 miles and 7,000 slowed ticks, a small, real, measured debt owed by every moving thing in this universe to the same unyielding rule. Whether it happens to be a subatomic particle, a jet full of passengers, or a man who spent the better part of 2 years deliberately orbiting his way into tomorrow. Set every other thought aside for a moment and notice what is actually happening in this room right now at the level of physics rather than furniture. Photons are arriving from a lamp, from a screen, from moonlight leaking through a curtain, from the faint glow of a charging light across the room. Each one left its source, crossed whatever gap separated it from its destination, and struck something. A wall, a page, the back of an eye. Trillions of these tiny events are happening in any given second, each one completing a journey that, from the room's point of view, took a measurable, if tiny, slice of time. The eye alone receives something on the order of 10 quadrillion photons every second in an ordinarily lit room, a number too large for any nervous system to count individually, which is exactly why it registers as a single, smooth, continuous scene instead of what it actually is, an incomprehensibly large crowd of individual arrivals assembled by a brain into the illusion of one continuous now. From the photon's own side of that same journey, the side physics can describe mathematically but never observe directly. None of that time passed at all. Not a fraction. Every photon touching this room tonight, from the reading lamp to the moon, carries the exact same undefined, nothing discussed for the entirety of this episode. A clock that isn't slow, isn't fast, isn't even zero. A clock the mathematics refuses to write a value for. You are, at this moment, sitting at the receiving end of an uncountable number of these undefined nothings, arriving continuously, forming everything you can currently see. The room is not being shown to you after a delay measured in undefined nothing. It only feels instantaneous because the delays involved are too small for a nervous system built on a much slower timescale to register. But the structure underneath that feeling of instant, effortless seeing is built entirely from journeys that, for the travelers making them, were never journeys at all. Every single one of them, from the reading lamp 3 feet away to the star overhead, made the exact same trip in the exact same way. Completely, without exception, without a single fraction of a second unaccounted for on its own side of the delay. Look up, if possible, at whatever slice of sky is visible from where you're lying. Somewhere in it, whether it can be named or not, is starlight that left its source before recorded history began, arriving now, tonight, carrying the same undefined nothing as the lamp across the room. Distance did nothing to change what the light itself experienced on the way here. Only the size of the delay changed, growing from nanoseconds to minutes to centuries depending on the source. And that delay belongs entirely to the one receiving it, measuring it, waiting through it. It has never once belonged to the light itself. Hold that for a moment. Everything ever seen by anyone has arrived by a method that, from its own side, never had to arrive anywhere, because it never actually left. Here is a tension tonight has not tried to resolve, and will not resolve now. The same undefined nothing that makes light indifferent to distance, indifferent to duration, indifferent to 14 billion years or 4 feet, is the exact thing connecting every point in this universe to every other point without exception. Light does not care how far it travels, because from its own side, it never travels at all. That indifference is total, mechanical, uninterested in whether it is crossing a room or crossing a galaxy, whether it is arriving at a sensor on a spacecraft, or the retina of something that will remember having seen it. And yet that same indifferent, uncaring nothing is the only reason a star's light ever reaches an eye, the only reason the sun ever warms a face, the only reason any 2 points in this entire universe are ever in contact with each other at all. The indifference and the connection are not 2 separate facts sitting side by side. They are the same fact, looked at from 2 directions. Nothing about light's undefined relationship to time and distance was designed with warmth in mind. Physics does not do anything with warmth in mind. And yet that same cold, uncounted, undefined nothing is the entire mechanism behind every act of seeing, warming, and reaching across space that has ever happened to anyone, anywhere. You did not choose this connection, and neither did anything else it reaches. It was built into the structure before there was anyone around to be grateful for it, or bothered by it, or even aware enough to ask whether gratitude was the right response at all. It simply runs, the same way it has always run, whether or not there is a you on the receiving end to notice. This is, in the end, close to the difference between calling the universe, and calling it our universe. Nothing about the physics changes between those two words. The mechanism is identical, indifferent, undefined, exactly as uncaring in one description as the other. What changes is only where a person chooses to stand while looking at it. Inside the mechanism, treating its total indifference as a kind of company, or outside it, treating the same indifference as a kind of exile. Physics will not make that choice. It never has. And no equation covered tonight has ever specified which way a listener ought to feel about it. A silence in the mathematics that matters more, right now, than almost anything already declared as fact. Tonight will not resolve which description is the true one, the mechanism that does not care, or the connection that makes everything reachable. Sit inside that tension instead of trying to close it, because closing it would mean picking a side the physics itself refuses to pick. The same photon that cannot be said to travel, in any sense a clock would recognize, is the photon currently allowing this sentence to be read, this room to be seen, this night to be shared with whatever is nearby. Cold mechanism, warm consequence, both at once, forever, in every act of light this universe has ever produced. Everything covered tonight, the mirror clock, the muons, the accelerator that will never finish its last inch, the airline clocks, the block universe, the timeless master equation has been circling the same reorganization without quite landing on it until now. Here it is, stated plainly. Nothing in this universe actually crosses distance, not the way it feels like it does. Every object with mass moves through the combined structure of space and time at a single, fixed total rate. The same rate for everything, always, without exception. What differs between objects is only how that fixed rate gets divided between the space part and the time part of the journey. Something sitting still on a couch is spending nearly all of that fixed rate moving through time, and almost none of it moving through space, which is why a clock on a couch ticks at very close to its fastest possible pace. Something moving near the speed of light is spending almost all of that same fixed rate moving through space instead, leaving almost nothing over for moving through time. Exactly why the muons clock ran slow, why the accelerator's protons clock ran 7,000 times slower, why a mirror clock on a fast-moving train ticked less often than the identical one standing still on the platform beside it. But push that trade to its absolute limit, and light is not a special exception to this rule. It is the rule's most extreme, most complete expression. Light spends the entirety of its fixed rate moving through space, and reserves none of it, not a sliver, not a fraction, for moving through time. That is not a flaw in light's design, or a strange edge case physics stumbled into by accident. It is the same single trade every object in the universe is always making, pushed all the way to one end of a scale that every moving thing in existence sits somewhere along. You are, at this exact moment, making that same trade, spending your own share of the fixed rate almost entirely on moving through time rather than space, drifting through the next second at nearly its maximum possible pace, precisely because your body is moving through so little space to get there. The photons carrying this story to whatever is displaying it have made the opposite trade completely, without exception, the entire way. The reorganization tonight has been circling as this. Light does not fail to experience time because it is missing something ordinary objects have. It experiences none of it because it has spent the entire allowance on the other half of the same transaction. The half every one of tonight's mysteries turned out to be measuring, from a mountain in New Hampshire to a tunnel outside Geneva, without ever quite naming what was actually being traded. This single idea is why a physicist can look at a spacecraft, a cosmonaut, a beam of gamma rays climbing a tower, or a particle circling underground at close to the speed of light, and describe all four with the same equation. Nothing about the mechanism changes from one case to the next. Only the proportion changes. How much of the fixed rate went to space, and how much was left over for time. Look back across everything tonight has measured, and a single trade-off explains all of it, top to bottom, without exception. The nanosecond delay of a face across a table, the 8-minute delay of sunlight, the 640-year delay of Betelgeuse, and the impossibility of ever pinning down a single, agreed right now for a star that far away, the 9-time survival factor of a muon, the 7,000-fold slowdown of a proton that will never quite finish the last inch of its own acceleration, the 60 and 270 billionths of a second gained and lost by clocks flown in opposite directions around a planet, the 38 microseconds a day quietly corrected in every phone's navigation chip. Every one of these numbers is the same underlying trade, measured at a different point along the same scale. How much of a fixed cosmic allowance was spent on space, and how much was left over for time. At one end of that scale sits something at rest, spending everything on time. At the other end sits light, spending everything on space. Between those two ends sits every other moving thing that has ever existed. Every muon, every proton, every airplane, every person, every star, each one making the identical trade in a different proportion. None of them exempt, none of them special, all of them measured by the same single rule. This is the finish line tonight has been walking towards since the very first minute. Not a single new fact, but the recognition that every fact already covered was the same fact, wearing a different number. But a finish line is not the same as an ending, and there is one more piece of the trade that hasn't been named yet. The part that turns this from an interesting equation into something worth carrying into sleep. You have spent this entire night as the object at the far end of that scale from light, not because you are unusual, but because lying mostly still means spending almost the entirety of your own fixed allowance on moving through time, second by second, at very nearly the fastest rate a clock is capable of running. Light has spent tonight, and every night, and every year since it was emitted, at the opposite end entirely. Two ends of one scale, one rule, holding both of you and it in place. Together, without exception. Every curiosity gap opened tonight. The muon, the proton, the block universe. The timeless equation was a different door into the same room. Walking back through all of them at once is what makes the room recognizable at last. Not a collection of separate strange facts about light, but a single strange fact about the whole universe. One that light simply demonstrates more purely than anything else inside it. The cosmonaut spending 800 days in orbit. The gamma ray climbing a 74-foot tower. The twin returning younger than the one who stayed behind. None of them needed a separate explanation. They needed the same one, applied at a different distance from the far end of the scale where light has always stood alone. So, how can light travel if it doesn't experience time? It travels the only way anything in this universe has ever traveled, by trading its fixed allowance of space and time for motion, spent entirely, without division, on the space half of that trade, leaving nothing behind for the half that would have let it experience a journey at all. It travels the way every accelerated proton under the Alps almost manages, pushed to within 7 decimal nines of the same trade, and still falling short, because falling short is the only option available to anything carrying mass. It travels the way a muon barely manages for 9 miles, borrowing extra time from the same fixed allowance, at a cost proportional to how close it comes to spending everything on space, the way light always does, completely, without the extra cost. It travels the way the equations governing a light clock demand, not as an approximation or a rough figure of speech, but as a mathematical limit every serious attempt to describe it arrives at and then honestly declares undefined. Because experiencing a journey was never part of what spending an entire allowance on space was going to leave room for. Light does not travel despite not experiencing time. It travels because it does not experience time. The absence is not an obstacle the physics works around. It is the mechanism, which leaves one sentence to replace the one this entire episode opened with. Light is not a traveler that, strangely, skips the experience of its own journey. Light is the part of this universe that reveals every journey was always a local transaction between an object and its own slice of time. And light is simply the object that never opened an account in that currency to begin with. You have never once seen the present moment shared in the way it always felt like it should be shared, with anything you were looking at. Not because sharing a present moment is rare, or difficult, or reserved for the very fast or the very still. It is because there was never a single, universal present moment on offer to share in the first place. Light was never traveling. You were always the one moving through its single, endless instant, carrying your own fixed allowance of time, second by second, while the light simply waited, undefined, exactly where it had always been. But none of this closes the door tonight opened. The block universe remains contested. The timeless master equation remains unresolved. Whether time is fundamental or assembled out of something deeper is still, tonight, an open argument between serious people who agree on every experiment and disagree about what all of it means. What changes is only this: the strangeness of a single kind of particle, examined closely enough, turned out to be the plainest window available into the strangeness of everything else. Including the very sense of now this sentence just finished arriving in, we have drifted tonight through a room lit by undefined nothings, across a mountain in New Hampshire, a tunnel outside Geneva, a train platform that never stops teaching physicists what, at the same time, actually means. We have wandered past a star that might already be gone, past two pedestrians who will never agree on what Andromeda is doing right now, past an equation for the whole universe that forgot to leave a place for time at all. We have followed a twin who came home younger, a cosmonaut who is technically the fastest time traveler alive, a beam of gamma rays climbing 74 feet toward a slightly different kind of now. None of it was ever, in the end, about light. It was about the strange, undefined nothing at the very edge of what a clock can describe, and about the much less strange, much more forgivable thing sitting on this side of that edge, still ticking, still moving through time at nearly its fastest possible pace, still here, still spending its own small share of the same fixed allowance every falling muon and every orbiting cosmonaut has ever spent. You are not separate from any of it. The photons that let this story reach you, the muons still falling through the atmosphere above the room, the light from a star that may or may not still exist, all of it moves through the same universe you do, obeying the same single rule, spending the same fixed allowance in whatever proportion its speed demands. Tonight does not ask you to understand all of that completely before you're allowed to rest. It only asks you to notice, once, that the light in the room and the body lying beneath it were always making the same trade, from opposite ends of the same scale. If your eyes feel heavy, let them close. That was always the plan for tonight, long before the first mention of a mirror clock or a mountain in New Hampshire. If this felt like the kind of night worth returning to, leave a comment when you wake up, where you were, what time it was, what you were still thinking about as the room went quiet. And if you're still here, still awake, still turning the trade between space and time over in your mind, the next chapter is waiting whenever you are. The universe will still be here when you wake up. So will we. Good night.